This is the last video in section 7, which is the section on chemical bonding, or an introduction to chemical bonding, and this one's going to be on covalent compounds. I'm not going to bother reviewing definitions of bonding, you know that. Let's think about chlorine gas. Chlorine, when it exists by itself, does not exist as individual atoms. It exists as chlorine molecules, Cl2. How do the chlorines bond together? Well, if you take two chlorine atoms, they each have, obviously, 7 valence electrons. If you try to bond these ionically by moving an electron from one chlorine to the other, we see that the chlorine on the left now has 8 valence electrons, and it's going to have a 1 minus charge. The chlorine on the right has lost an electron, so it's going to have a 1 positive charge, but it does not have an octet. This is not going to work. So in nature, what really happens is the two chlorine molecules get very close together, and they share a pair of electrons. This is what a covalent bond is. By sharing this pair of electrons, each chlorine appears to have an octet, and therefore the rule is satisfied. So remember, covalent bonds, you share electrons. Now it turns out that covalent bonds will occur only between nonmetals. And as a quick reminder, the nonmetals are the elements to the right of the staircase. There's not a large number of them. And we want to draw out what the molecule looks like. Covalent bonds are represented by a straight line. So we come back to our chlorine molecule, which has the pair of electrons bonded. We would draw the bonding like this, and we would say this is a single bond. Single bonds, 2 electrons are shared. Well, what about sulfur? Sulfur has 6 valence electrons. Really can't make an ion out of this for the same reason you couldn't with a chlorine, but if you share 2 pair of electrons, you now have a double bond, which would be shown like this. Double bonds, there are 4 electrons shared. Phosphorus has 5 valence electrons. You can share 3 pair, that's a triple bond, and it will be demonstrated like this. Next, go to carbon. You see that there are 4 valence electrons, but there's no such thing as a quadruple bond. This actually means that carbon can bond with more than one thing, and is actually the whole basis behind an entire branch of chemistry called organic chemistry, of which biochemistry, the things that keep us alive, is a subset. So we are carbon-based life forms because of the versatility of carbon being able to covalently bond in multiple ways. And carbon can form up to 4 bonds, so it can join up with up to 4 different atoms. So as we just demonstrated, covalent bonds can have multiple bonds, and they can be shared in combinations. For example, nitrogen can bond with 3 hydrogens, and this is actually ammonia, or nitrogen could double bond with an oxygen and a hydrogen, and there are multiple other combinations. Covalent bonding is much more versatile than ionic bonding, where ionic bonding has fixed ratios. Now, covalent compounds do exist as molecules. They can be freestanding molecules, which means they have a molecular formula. And it's important to remember that a molecular formula is just an inventory of the atoms for a specific compound. And it does not have to be the lowest whole number ratio, unlike ionic formula units. So for example, water, H2O, tells us that we have 2 hydrogens and 1 oxygen. No subscript means the subscript is 1. And the subscript always applies to the element directly to the left of the subscript. So here we have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And there are a number of compounds that this could be, because the molecular formula does not tell you how the molecule is put together. It's just an inventory. So if you're given this molecular formula of 2 carbons, 6 hydrogens, 1 oxygen, sometimes you might say it is C2H6O or O1, there are actually 2 possible combinations. One is ethanol, the other is called dimethyl ether, and they have very different physical properties. They have very different chemicals, though they are made up of the same elements. think about making multiple structures out of Lego blocks. Now, covalent compounds, unlike the ionic compounds, exist as solids, liquids, or gases at room temperature, depending upon the compound. Because you know that sugar at room temperature is a solid, water is a liquid, and chlorine is a gas. Compared to ionic compounds, most covalent compounds have lower melting points and boiling points. Covalent compounds do not ionize when dissolved in water. This means they do not conduct electricity, and they are called non-electrolytes. And almost all of the covalent compounds are poor conductors of electricity and heat, no matter what phase. But a pure carbon covalently bonded compound can be an exception here. And actually, a couple of years ago, some folks won the Nobel Prize for graphene, which is covalently bonded carbon in hexagon shapes, one atom thick. This is very good conductor of electricity, very, very flexible, very, very strong, and people are talking about this revolutionizing our electronics. So to review covalent bonding, covalent bonds share electrons. There is no charge involved with covalent bonds. They are between non-metals only. If a metal is present, then there's an ionic bond. Ionic bonds can be multiple. They have various phases at room temperature depending upon their structure. They tend to have lower melting points and boiling points. They are usually poor conductors of electricity and heat, no matter what the phase, except for carbon. And they do not ionize. Remember, this is also called dissociating when they are dissolved in water, and so they are called non-electrolytes. They do form individual molecules, and that pretty much covers it. So we will be off to section 8 next. In section 8, we're going to discuss how to name ionic and covalent compounds and go more into how you combine them.